Hello, Precalculus students. This is Mrs. Raposa, and this is your lesson on section 4.5, inverse functions. You probably didn't get pre-made notes, but that's okay. You can take notes on graph paper if you have it, because we will be graphing. However, if you don't have graph paper, taking notes on plain paper or line paper will work just fine. There'll be 6 examples total, but a lot of them are repeaters. You'll see what I mean, so it won't involve that much writing. Examples A and B are review from Algebra 2, and examples 1 through 4 are more pre-calculus level. And don't forget you can stop the video at any time and review anything you didn't catch the first time, or pause it so you can get some notes down. Let's get started. So first of all, let's talk about what inverse functions are. Inverse functions undo one another. For instance, division by 2 is undone by multiplication by 2. Subtraction of 5 is undone with addition of 5. So that's what we mean by inverse functions. And you may see this notation. It looks like f to the negative 1, but that negative 1 is not an exponent. It's read f inverse of x. Perhaps you remember that from Algebra 2. So that really stands for the inverse function of x. Let's start with example A. Graph f of x and its inverse on the same coordinate plane. When you're asked to do this, it is a good idea to set up a table of values where you choose values of x, and then we're going to choose I chose these 4 numbers to plug in. You can choose any 4 numbers for x as long as they're in the domain of f of x. And then we'll calculate what f of x is. The next thing you want to do is set up another table of values for points that are going to be on the inverse function. So graphing a function and its inverse on the same coordinate planes requires a table of values for f of x and another table of values for f inverse of x. So let's plug in 0 for x into this function. When x is 0, we get that f of x is negative 1/2. So f of 0 is equal to negative 1/2. So the point 0, negative 1/2 is on the graph of f of x. Perhaps you remember when you graph an inverse function that you just swap the x and y coordinates, or swap the input value with the output value. So 0, negative 1/2 on the graph of f of x means that negative 1/2, 0 is on the graph of the inverse function. The fact that f of 0 equals negative 1/2, that is going to imply that f inverse of negative 1/2 equals 0. Notice how the input became the output on the inverse function, and the output on f of x is now the input for f inverse of x. Before we go on, you may want to stop the video and make sure you have these 2 tables of values in your notes and this function. It would also be a good idea to write this sentence down at the bottom so that you understand that the input and output change places in the function notation for f of x and f inverse of x. Let's try different values now for x. We're going to do f of 3 this time. That will give us 3 minus 1 over 2, which will be 2 over 2, which is 1. So 3, 1 is on the graph of f of x. That implies that 1, 3 is on the inverse function. And again, the function notation. If f of 3 equals 1, then we know that f inverse of 1 is going to equal 3. We'll plug in 5 for x, and we'll get that f of 5 is 4 over 2, which is 2. So 5, 2 is on the graph of f of x, implying that 2, 5 is on the graph of the inverse function. And again, when we plug in 8, we'll have 7 over 2 for f of x, which is 3.5. So when x is 8, f of x is 3.5. That means that 3.5, 8 is on the inverse function. And again, the function notation, if f of 8 equals 3.5, then f inverse of 3.5 equals 8. Now let's plot these points on the coordinate plane, because that was the purpose of coming up with the tables of values, 2 of them. We'll plot the points for f of x over here and draw the line that goes through them. That is a linear function. You may not recognize that, but that is 1/2 of x minus 1/2 when you divide x over 2 and negative 1 over 2. And I can see that the y-intercept is negative 1/2, and the slope is indeed 1/2 mx plus b. So we go up 1 and over 2, and we'll come to this point. If you start from here, you can go up 1 over 2. You see that the line has a slope of 1/2. That's besides the point. You don't need to write that down, but that is just another way of writing f of x. When we plot the points on the inverse function, we have these points and draw the line that goes through them. And that is the graph of y equals the f inverse of x. Don't forget that any function and its inverse graphed on the coordinate plane will be reflections of one another over the line y equals x. So to obtain the graph of f inverse of x, just reflect the graph of f of x over this line, this slanted line, y equals x. You may recall that from Algebra 2. So let's take a look at example B now. We're going to find a rule for f inverse of x, which just means a function, so some equation for f inverse. Remember that this is the graph of f inverse of x. We're going to come up with an equation for that line. It is linear, so we'll know we'll come up with a linear equation. So if you recall from Algebra 2, the steps in finding the inverse function is, first of all, if it's in f of x form, just replace the f of x with y. So we'll have y equals x minus 1 over 2. And please write down the steps as we go through the process and show the work in your notes for how we found the inverse function. Step 2, swap x and y. So we'll have x equals y minus 1 over 2. Step 3, solve for y. So get y by itself on one side of the equation. I'm going to start doing that by undoing the division of 2 with multiplication of 2 on each side. On this side, multiplication of 2 and division of 2 undo each other, and I end up with 2x equals y minus 1. Now to get y alone, last step is to add 1 to each side, and I have 2x plus 1 equals y. So this is my inverse function. Y equals 2x plus 1. So we can always do step 4 if we want to put it into function notation. We can replace the y with f inverse of x, because this is the inverse function, and say that f inverse of x is equal to 2x plus 1. If you go back to example A, where we graphed the inverse function and f of x, you can see that this is indeed the graph of y equals 2x plus 1. The y-intercept will be 1, and it is, and the slope is 2, and it is. It goes up 2 over 1. So that's a good way to check to make sure that you have the correct inverse function if you have a visual of the graph in front of you. Another way to check is looking at the table of values. When you use these values for x, you should get these values for y, and we do. If x is negative 1/2, 2 times negative 1/2 is negative 1, and negative 1 plus 1 does give me a y value of 0. When x is 1, 2 times 1 plus 1 is going to give me 3. It works. And you'll see that when you use 2, you get 5 for f of x, and when you plug in 3.5 for x, you will get 8 for f of x. So that's another way of checking to make sure that you have the correct inverse function. Okay, the following statement I'd like you to copy into your notes, please. And that statement says, two functions f and g are inverse functions if the following statements are true. And the first statement says that g of f of x will equal x. And that's for all x that's in the domain of f. Okay. And also, f of g of x will equal x for all x in the domain of g, the inner function. So doing composition, g of f of x and f of g of x will both result in x. So if you're asked to verify that two functions are inverses of one another, you have to do two function compositions. One of them will be showing that g of f of x equals x, and another function composition showing that f of g of x is also equal to x. Notice for example 1, I've chosen to use the functions that we did in examples A and B. So we already use these equations, and I know that this function is the inverse function of this one. Before we called it f inverse of x, now I'm just calling it g of x. So let's go ahead and show that g of f of x does equal x. G of f of x is equal to g of x minus 1 over 2, because that's what f of x is. That means I go to the g function, and I replace every x with what's in the parentheses here. So in the g function, here's my x, and I'm going to replace that with x minus 1 over 2. So I'll have 2, and then in parentheses, the fraction x minus 1 over 2, and then plus 1/2. Plus 1. Here it is right here. So simplifying that, you'll see that the 2's cancel, and I end up with x minus 1 plus 1. And negative 1 cancels positive 1, and I'm just left with x. So yes, g of f of x does equal x. Now let's do the function composition the other way as well. Show that both are true. So f of g of x will be f of 2x plus 1, because that's what g of x is. That means that I'm going to look at the f function, and everywhere there's an x, I'm going to replace that x with the expression 2x plus 1. So we'll end up with 2x plus 1 minus 1 in the numerator divided by 2. Simplifying this, I can see that the positive 1 cancels the negative 1, and I end up with 2x over 2, which does simplify to x. So yes, f of g of x also equals x. So because g of f of x equals x, which is also equal to f of g of x, that means that these two functions are inverses of one another. And that's how you verify that two functions are inverses of one another, by doing two separate function compositions and showing that they both result in x. For example 2, we're asked to sketch a graph of f of x equals 4 minus x squared and show its inverse is not a function. We're going to use something called the horizontal line test to show that. You've heard of the vertical line test before, but this is something a little different. This is a parabola facing downward because the leading coefficient is negative 1. So the graph looks like this. These points are on the graph of f of x. You can verify that on your own. Notice that f of negative 1 and f of positive 1 both result in a y-coordinate of 3. And that's using the order of operations. You have to square the number first and then subtract from 4. So negative 1 squared and positive 1 squared are both 1. So either way, you get a y-coordinate of 3. That means that this y-coordinate of 3 is assigned to two different x-coordinates. Although this graph is a function, it passes the vertical line test, it's not a one-to-one function. Notice it fails what we call the horizontal line test. A horizontal line passes through more than one point, just about everywhere on the graph here. So it's not a one-to-one function. If we were to look at points on the inverse function, or the inverse relation I should call it, by swapping the x and y coordinates, you'll see that we're going to have some x coordinates that are assigned to two different y coordinates, which means this is not a function, because where x equals 3, we get negative 1 for y and positive 1 for y. So this fails the vertical line test. Every input on a function should have just one output. So that's not the case here. It fails what we call the vertical line test. So this is not a function. Video 2 will pick up where this video left off, but right now, stretch break.